Welcome to Chapter 1, Real Numbers, a chapter that deepens your understanding of the number system you have worked with since childhood and takes it to a new level of rigor and beauty. Consider a unit square. Each side has length 1. By the Pythagorean theorem, a squared plus b squared equals c squared. Substituting 1 and 1, the diagonal d equals root 2. The ancient Greeks assumed every length could be expressed as a simple fraction. But root 2 shattered that belief. It cannot be written as a fraction. This was the first crack in their mathematical worldview and the beginning of irrational numbers. We are going to prove that root 2 is irrational. We use a technique called proof by contradiction. We start by assuming the opposite of what we want to prove. Assume root 2 equals p divided by q. Here p and q are integers with no common factor between them. Now we square both sides. Rearranging gives p squared equals 2 times q squared. This tells us that p squared is an even number. And when a perfect square is even, its square root is also even. So, p must be even, and we can write p as 2 times q. Substituting back, we find that q squared is also even. So q is also an even number. But wait, both p and q are even. That means they share the factor 2. But we assumed p and q share no common factor. This is a contradiction. Our original assumption must be wrong. Therefore, root 2 cannot be written as a fraction, and it is irrational. This is the real number line. It stretches infinitely in both directions. Every point on this line corresponds to exactly one real number. Some of those points are rational numbers. Rational numbers can be written as a fraction. For example, 1/2, 1/3, and whole numbers like 1, 2, and 3. But rational numbers leave infinitely many gaps on the line. Those gaps are filled by irrational numbers. Root 2 sits between 1 and 2. Root 3 sits a little further to the right. P sits just past 3. These numbers have decimal expansions that go on forever, and they never repeat. Together, rational and irrational numbers fill the line. Not a single point is left out. At the innermost level, we have the natural numbers, represented by n. These are the counting numbers, 1, 2, 3, and so on. Surrounding them are the integers, represented by z. Integers extend the natural numbers by including 0 and negative whole numbers like -1 and -2. The next layer is the rational numbers, represented by q. These include all fractions, such as 1/2, 0.75, and -3, 4. Every integer is also rational. Finally, the outermost set is the real numbers, represented by r. Beyond the rationals live the irrational numbers, such as root 2, root 3, and pi I. They cannot be written as fractions. Together, rationals and irrationals fill the entire real number line. This chapter has 4 sections. Each section builds on the previous one. The first section is called Euclid's division algorithm. Euclid was an ancient Greek mathematician. His algorithm is a step-by-step method. It finds the highest common factor of any 2 integers. It does this using repeated division. The second section is the fundamental theorem of arithmetic. Every integer greater than 1 can be broken into prime numbers, and that factorization is always unique. The third section revisits irrational numbers. We build formal proofs using contradiction. We show that the square root of any prime is irrational. The fourth section is about decimal expansions. We connect prime factorization to decimal representation. Some fractions give terminating decimals. Others give decimals that repeat forever. The real numbers are defined as the union of the rationals and the irrationals, two infinite families of numbers, interleaved so densely that together they cover every single point on the number line without a single gap. This chapter will sharpen your tools for working with them. Numbers have secrets. Mathematics reveals them. Let us begin.